This is Professor Derf Seitz. This algebra tutorial is the first of 4 parts that focus on solving quadratic equations. Part 1 is using factoring to solve them. Quadratic equations in standard form are of the form ax squared plus bx plus c equals 0, where x is the variable, we see to the second power here, and a, b, and c stand in for actual values. Notice that the right-hand side is equal to 0. If your equation does not have 0 on the right, you need to rearrange it to an equivalent equation having 0 on the right. You do this by multiplying or dividing both sides by the same thing, adding or subtracting both sides, the standard manipulation rules for equations, combining like terms, distributing, and the like. To factor means to write as a product. We're going to be using the zero factor property. If we have a product AB equal to 0, this implies that we can set each of the factors equal to 0, or both of them could be 0. It's equivalent. So we take this equation here and it becomes 2 simpler equations. That's the key technique here in this factoring solution. We will use some factoring patterns. There are many factoring patterns. The most common ones that we'll focus on here in this tutorial are the greatest common factor. This is reverse distribution. We're taking AB plus AC and factoring out the A, and we see if we distribute back we would get AB plus AC. If we have the minus sign, similarly we factor out the common A and get B minus C. So in this little distribution example here, A is the greatest common factor. We'll use difference of 2 squares. A squared minus b squared becomes the product of 2 binomials, a minus b times a plus b. There are 2 perfect square trinomial patterns. A squared plus 2ab plus b squared becomes this binomial squared, which is the product of the binomial times itself. It's a product. And its cousin pattern has a minus here. And you get the minus squared. We'll also be factoring trinomials using reverse FOIL. FOIL is a shorthand for multiplying 2 binomials together. If we multiply them out fully using distribution, we get a times c plus a times d, and b times c plus b times d. If we group the middle 2, then it shows how we get a trinomial back. The AC is the first term of this binomial and the first term of that binomial. The BD is the last of each of the binomials. And in the middle we have the sum of AD, which is the outermost terms, and BC, which are the innermost terms. And we get FOIL. So to take a trinomial and factor it using reverse FOIL, we move backwards towards the product of 2 binomials, making use of the fact that the first and the last have to be first and last, and the middle term of the trinomial has to be the sum of the outer products plus the inner products. Our first example is the greatest common factor. 8x squared minus 4x equals 0. The greatest common factor is 4x. Bringing that out, we get 4x times 2x minus 1 equals 0. You can always check, you multiply back. 4x times 2x is 8x squared. 4x times minus 1 is minus 4x. Now we apply the zero factor property. We have a product equal to 0. We turn it into 2 simpler equations, 4x equal to 0 or 2x minus 1 equals 0. Solve each of these, divide by 4 over here on both sides, x equals 0, add 1, and then we get 2x equals 1, divide by 2, x equals 1/2, 2 solutions to this quadratic equation. Example 2, a difference of two squares. 9x squared equals 49 is not in standard form. We subtract 49 from both sides to get 0 on the right. Rewriting 9x squared as 3x in parentheses squared and 49 as 7 squared, we clearly have matched the difference of two squares pattern. Applying it, we get 3x minus 7 times 3x plus 7. Breaking this into the two simpler equations using the zero factor property, we get 3x minus 7 and 3x plus 7 equals to 0. Add 7 divided by 3, subtract 7 divided by 3. Our two solutions are 7/3 and minus 7/3. A perfect square trinomial is example 3. This is a perfect square. 25 is 5 squared. The coefficient of the first term is 1. So the product of 1 and 5 is 5. The middle term is twice it, 10 with a minus sign, so it matches the perfect square trinomial pattern. We apply the pattern and we get x minus the 5, which was 25 is 5 squared. X minus 5 squared equals 0. That's x minus 5 times x minus 5. If we break those apart, we get identical, simpler equations. X minus 5 equals 0. This is called a double root. Each one gives us the 5, but since it appeared as a factor twice, it's called a double root, even though there's a single solution. Example 4, reverse FOIL. We have x squared minus x minus 6 equals 0. First we create our two binomials, and the first terms have to be x because they have to multiply to x squared. To get to minus 6, we can try 6 and 1 or 2 and 3, but the 2 and 3 gives us a better opportunity for the middle term. Multiplying the 2 times the negative 3, we get the negative 6. Checking the outer, x times a minus 3x times a minus 3 is minus 3x, and the inner 2x is plus 2x. Minus 3x plus 2x is minus 1x or minus x. Breaking it apart, x plus 2 is 0, x minus 3 is 0. We get x equals negative 2 and x equals 3. Example 5, another trinomial using reverse FOIL. This one's more difficult because there's more possibilities. 8x squared minus 2x minus 21 equals 0. We look at factors of the leading term, coefficient 8, and of the last term, 21. So minus 21, but we're just looking for the numeric factors. So the 8 is 8 and 1 is a possibility, or 2 and 4. And the 21 is 21 and 1, or 3 and 7. We want to pair these in such a way as so we can get a minus 2 in the middle. The 2 and 4 and the 3 and 7 can be paired. If we take the 2 and the 4 as first things, and then the 7 and the 3, 2 times 7 will be 14, and 4 times 3 will be 12, and there's a difference there of 2. So let's try this out. We take the 2 and the 4 as the first terms. 2x times 4x gives us the 8x squared. Notice the last terms, the 3 and the minus 7 give us the minus 21. So there was the 2 and the 4 and the 3 and the minus 7. Now let's check the outer. The outer 2x times negative 7 is negative 14x. And 3 times 4x is plus 12x. Add those together and you get a minus 2x. This works. Breaking those apart, 2x plus 3 equals 0, or 4x minus 7 equals 0. Subtract 3 and divide by 2. Add 7 and divide by 4. We get our two answers, negative 3 halves and 7 fourths. Example 6. Simplify first. Each term in this left-hand side and also the right-hand side are divisible by 2. So we're going to divide the entire equation, both sides, by 2, which divides every term over here by 2. We get this simpler quadratic equation. You always simplify first. Taking this one, we look for factors of 28 We'll use 4 and 7 because they have a difference of 3. We'll pick our signs appropriately. So here we have x and x is x squared. 4 and negative 7 gives us a negative 28. And then for the middle term, we take the outers, negative 7x, the inner, positive 4x, add them together, we get negative 3x. Breaking these factors apart, x plus 4 is 0, and x minus 7 is 0. This becomes negative 4, this becomes 7. Our last example is a combination, and it's also not quadratic to begin with, but we can solve it by using what we've learned using factoring. So we're going to take out a GCF first. The GCF of the left-hand side is 2x, leaving us with x squared minus 9 equals 0. Now we have a product. We apply the zero factor property. On the left, we get 2x equals 0, and or x squared minus 9 equals 0. The 2x minus 0 divided by 2, we get x equals 0. Over here, we rewrite the 9 as 3 squared. We have a difference of 2 squares. That becomes x minus 3 times x plus 3 equals 0. Breaking those apart, x minus 3 is 0, x plus 3 is 0. Here we have 3 and negative 3. And notice 0, 3, and negative 3 are 3 solutions to this cubic equation. Factoring for certain types of problems, that if you can recognize that they can be easily factored, it's a very fast way to solve those kinds of quadratic equations.